Okay, so hello everyone, and in this video we'll be learning about tree data structure in JavaScript. This is a very popular kind of data structure which you will learn in normal programming. It's very important in developing software applications and also in competitive programming and also in developing applications like websites or mobile apps which use JavaScript. So it is a very important part in JavaScript also, because in JavaScript we use a lot of different kind of data structures for different purposes. Like we use arrays, we use linked list, we use stack and queues, and similarly we also use tree data structure in JavaScript. So why do we use this tree data structure in JavaScript? So there are actually many reasons for using it, and we'll be understanding what is actually tree data structure and why do we use the tree data structure. And obviously it will give us some more benefits than other data structure, and we'll know when to use this data structure and when to use other data structures. All right, so now before moving on, in the live chat you'll find a link of a course provided by Geeks4Geeks. That is a course for data structures with algorithms using JavaScript. So if you visit that link, you can also check that link in the description. Okay, so if you visit that link, it will take you to a page like this. So this is a recent course, and all the latest things which are introduced in JavaScript along with data structures and algorithms are available here. So you can check out this one, and this is actually a paid course. So you can see that what all things will be covered while you study this, and also end-to-end support will be provided by Geeks4Geeks. You will get doubt assistant, a lot of things. You can check out this one. Okay, so it covers everything which is required in DSA for JavaScript. So not only for development or any mobile app application, JavaScript with DSA can actually be used in competitive programming also, because there are a lot of platforms which support JavaScript. So in those platforms, always you can actually use JavaScript because it's easier, and will be fun using JavaScript for competitive programming with DSA. All right, so you can check out this course also. Okay, so first of all, we'll begin with what is a tree data structure. Then we'll be knowing some basic terminologies which you need to know, learning tree data structure and kind of trees which we are going to build. Okay, so let's start. So first of all, what is a tree? So in terms of data structure, the data structure that represents hierarchical data, that means I am a parent, I have two children, they have more children, this is called hierarchical data. Okay, so this is basically represented in a format of tree. Okay, you can see that it's a tree format, or you can also refer this to as a file system, where you have a folder can have multiple folders, a folder can have multiple folders. So it's like a tree. It's like a you must have heard about network marketing. Okay, so network marketing, I don't know if it's good or not, but yeah, network marketing also uses this kind of tree format. They there is no specific criteria, I don't know any specific criteria, but one person will say that if three people will join that person, and similarly those three people will join other three persons, so that's how a tree becomes. Okay, so that's a tree data structure, a good example of tree data structure. Okay, so a tree data structure is a hierarchical structure that is used to represent and organize data in a way that it is easy to navigate and search. Okay, so the reason why are we creating tree data structure, because it becomes a lot more easier to search and navigate. Why it's easier? Because you can see that we are getting a tree format. Okay, we are getting a tree format, that means we can go in multiple directions, okay, in any direction. But in a linear data structure, like array or a linked list, we'll always move in one direction, right? But in tree data structure we can move in any direction. There are multiple kind of branches of a tree, you can move in any other direction. So a tree is known as non-linear data structure, and the benefit of using a tree is it makes things easier. Okay, so tree can be used in things which require hierarchical structure, like network marketing softwares, or you can consider a file system where you are storing your different folders in tree format, or you can say there are actually different kind of uses for tree data structures. Okay, so what does it actually looks like. So it's actually a collection of nodes you can just consider as some points, okay, some points, and they are interconnected with each other using edges. Okay, so there are different kind of trees which you can build, have some they have some rules, different kind of rules, like binary search tree can have at most two childs. We'll see that. Okay, so all the nodes are connected together by edges, by lines, okay, and they have some hierarchical relationship with each other. Okay, they can have some hierarchical relationship with each other, like suppose I have a number 2. Okay, so I can say that 2 can have two childs. What childs can it have? We can say that 2 can have a smaller number, that is 1, on the left side, and a bigger number, that is 3, on the right side. So you can see it has some relationship with the 2. Okay, number 2. So that's how we can actually use tree data structure for a lot of purposes. Okay, so now we'll be looking into some terminologies, how does it look, and what are the terminologies which you will be needing whenever you study it for your colleges or any competitive programming purpose. Okay, so you will be needing this kind of format so that you get a easier understanding what is what. Okay, so let's start. So as you can see, this is a very basic tree which I have created. There isn't any rule here. Okay, this is just a general tree. Okay, general tree data structure where you can get any number of nodes. You can see that A, B, C, D, E, F, G, all are nodes. Okay, so you can just say that your points are actually your nodes. All right, so the topmost node in any tree will always be known as root node. That is, A is our root node. Okay, so A is our root node, and then we have what? We have different kind of nodes here, you can see, but they have specific meanings. Okay, so you can actually make a lot bigger trees. Okay, but since we have to just explain a single part of a tree, so this is a very small tree, but trees are actually very big. Okay, very big, and a lot of companies are actually using trees for creating relationships with each others, like A is related to B somehow. Okay, so now let's talk about some more terminology. So the top one is known as the root node, and the bottommost, this F, this G and D. You can see D doesn't have any child, F doesn't have any child, G doesn't have any child. So D, F and G are known as leaf nodes. Also this C will also be known as a leaf node because they don't have any child. Okay, so this is the root node, these are the leaf nodes. Okay, last nodes or leaf nodes. So now what is a descendant? So a descendant is actually immediate successor of the given node. Okay, so suppose A is a node, right? It's a root node, but it can be considered as a normal node also. So the child of A is what? Child of A is B, child of A is C. Okay, so B and C are descendant of A because B and C are nodes of, are children of A. Okay, so here you can see B and C are descendant, or you can also call B and C as child node of A. So B is what? B is child node of A. C is what? C is child node of A. Okay, so I hope I am clear with this. So now you understood what is descendant and what is child node. They are same, just different wordings. Okay, so now what is a parent node? So here you can see that B is a node, right? And B has two children, that is D and that is E. So if I just ask, who is the parent of D? Who is the parent of D? So you'll always say B is the parent of D, right? Who is parent of E? B is parent of E. Who is parent of F? E is parent of F. Who is parent of G? E is parent of G. Okay, so you can see that these are just some terminologies. Now what is a sibling? So if I talk about sibling, it's simply that you can see B has two children. Okay, that is D and E. So they are actually siblings, right? They are siblings. So D and E can be considered as siblings. Similarly, F and G can be considered as siblings. Similarly, B and C can be considered as siblings. Okay, so these are the siblings. Now I told you what is the leaf node, that is D, F, G and C. Endpoints are always known as leaf nodes, which don't have any children are known as leaf nodes. Okay, so now what is an ancestor node? So if I talk about D, if I ask you who is ancestor of D, ancestor simply means their parent, parent of parent, and something like that. So you can see that D has a parent B. Okay, D has a parent B, and also you will count their siblings also. Okay, so parent B, B sibling is C. So these are ancestral nodes, and also above those are all ancestral nodes. So you can simply consider that above D, whatever are the nodes can be considered as your ancestral nodes. Okay, so these are some basic terminologies which you will need, because these terms are actually used a lot. Okay, so I hope you are clear with this, and if you have any doubts you can still ask me in the live chat. All right, so now we have covered the terminologies. Now one more thing, very important. If I ask you, suppose you have n nodes, n number of nodes, that is 1, 2, 3, 4, 5, 6, 7. Okay, you have 7 number of nodes. Okay, how many edges are there? 1, 2, 3, 4, 5, 6. So you can see that if you have 7 nodes, you will be having 6 edges, right? So it simply means that if you have n nodes, you will be having n minus 1 edges. All right, I hope it's clear. Now, what is depth of a node? Okay, depth of a node. So it can be defined as the length of path from the root to the node X. Okay, so if I talk about this node D, what's the depth? Or else if I talk about E, okay, if I talk about E is some node. What's the depth? So depth simply means the distance from the root to the edge, okay, to the node which I am talking about, that is from A to E. How the distance is calculated? By just calculating number of edges between them. So here you can see we have one edge from A to B, then we have one edge B to E. So you can see that the distance is actually 2, okay, 2 edges or 2. So you can see that depth is simply the distance from root to that specific node which you are talking about. Okay, so the distance is 2 here. Okay, similarly if I talk about G, so what's the distance? That is one edge, second edge, and third edge. So you can see that the distance is 3. Okay, so now if I talk about height of node, height of node, so height can be simply defined as longest path from the node. If I talk about height of B, height of B, okay, longest path the from any node. Okay, so if I talk about B, I want to know its height, so I will simply call the longest path. So you can see this is also a leaf, this is also a leaf from B to F, and from B to G is also a leaf. So B to D, B to F, and B to G are leaves, but I'll always consider the longest. Okay, so I can simply consider this one, this is the longest path, or you can consider this one also. So you can see that this longest path will be called height of B, that is 2 edges. Okay, 2 edges is the height of B. And similarly height of tree is what? So height of tree is similar, and it's actually, if I talk about the longest distance, that is the longest distance is from root. Height of tree will be considered from root, okay, from root to B to E to F, because this is the longest distance, or you could consider G also. So you can see the maximum number of edges are covered here. So this is the height of tree. Okay, so height of node is from any different node, height of tree is always from the root. Okay, so now what is a subtree? So you can see that this is a complete tree. Okay, this is a complete tree. Okay, so if I talk about A, it's a root node. I know it's a root node. Okay, so you will be given, it will be given that it's a root node, or you have some situation where you have to consider some starting point, that will be your root node. Okay, which covers everything. Okay, so you can see that A has some child B, D, E, F, G. So you can see that this is also a tree. This also looks like a tree. If I remove A and C, this bottom one also looks like a tree. So you can see that this is a subtree. B, D, E, F, G. This is a subtree. Okay, similarly, E, F, G is also a subtree. So you can see a tree can have any number of subtrees. Okay, so now we have covered basics of trees. Now I actually want to show you one article which is available in Geeks4Geeks. Okay, so for that you can simply type trees in data structure. Okay, trees in data structure. So you can see that we have this good article. You can see this article, and this is a very great diagram which they have provided. You can see that we have a very simplified diagram. Okay, you can see that it covers everything. You can see this and you can get a lot of idea what is what. So you can see we have a root, we have an edge which connects between both of them. Okay, and then you can consider this as a key. Okay, whatever is the value will be considered as a key. Okay, so you can see that we have a parent. If B is parent, then D and E will be childs, and D and E are interrelated to each other, that is they are siblings. Okay, so you can see that this is a very great diagram. You can check this. All right. So you can actually read this. That's a very great article. Okay, so you can see that they have covered a lot of topics, basic terminologies which we have covered right now. Then they have also told us the properties which we have covered right now. Okay, so they have also explained us why to use trees in data structure. So we'll be looking into those applications later on. Okay, so you can read this article as a summary of this video because it's a great article. Okay, so you can see from top to bottom they have explained everything. Okay, so now we'll continue. And before moving on, if you have any doubts, you can ask me in the live chat. Hi Adarsh, how are you? Okay, so now we'll continue. And okay, so now we'll continue. So next is why tree is considered as a non-linear data structure. First, you need to know what is a linear data structure. So a linear data structure is simply which is in a line. Okay, which is in a line. Okay, which does not have any specific branches. So a linear data structure can be counted like an array is a linear data structure. Linked list also is a linear data structure. Why they are linear data structure? Because we have items in a line. Okay, always in a line. So you can consider them as a linear data structure. Okay, what is a non-linear data structure? Simply an element can have multiple branches, multiple childs. That can be considered as a non-linear data structure. That means we don't have any specific rule for what, how many number of childs can it have and something like this. So that can be considered as a linear data structure. Okay, so a tree is considered a non-linear data structure because it does not follow a sequential or linear arrangement of elements. As you have seen before, that we don't have any linear sequential arrangement of elements. We have different elements separated, spread it out. Okay, so that's why tree is considered as a non-linear data structure. And in a linear data structure like an array or linked list, elements are organized in a linear order. Okay, if you know what is an array, if you know what is a linked list, you can say that they are actually in a linear order, right? So arrays and linked list are linear data structures. Elements are organized in linear order in them. Okay, one after the other, that is. So however, in a tree the elements are organized hierarchically. Okay, hierarchically. So sometimes it's very difficult to pronounce these words. So hierarchically. Okay, so in a branching structure, that means a tree has branches. All right, so I hope you got the difference between linear and non-linear data structure, and the tree is known as a non-linear data structure. So in a tree data structure, each element is called node. We know that nodes are connected by edges. We have each node connected with other node by a simple edge, which represent the relationship between the nodes. Okay, so the top one is actually called the root node. Okay, the top node, and which is the topmost node and serves as the starting point for the traversing of the tree. So nodes in a tree have childs nodes with them. So if A is the parent, then we have B and C as child, something like that. Okay, nodes below them are considered as childs, and any node can have a parent node, or a single node can have multiple childs also. Okay, so nodes without any child nodes are actually considered as leaf nodes. Okay, and nodes without any parent node can be considered as the root node. Okay, that means there will always be one root node. Okay, so I have seen some data structures which have two different parent nodes, but we'll be mostly covering one single parent node. Okay, so that will be our root node. So now the non-linear aspect of a tree arises from the fact that nodes can have multiple child nodes. Okay, that's why that is called non-linear data structure. And the relationship between node is not necessarily a simple linear progression. Relationship is not something which is pretty much defined. Okay, the relationship can be anything, okay, unpredictable sometimes. So that's why it's non-linear. Each node in a tree can have zero or more childs, forming a branch structure that allows for a more complex organization and representation of data. Okay, so this non-linear data structure makes trees particularly useful for representing hierarchical relationships. Okay, if you have any kind of file system organization, or if you have DOM manipulation, we must have heard about in HTML, CSS, JavaScript, something about DOM. Okay, so it's actually using a tree structure. So if I go to Google and if I take you to some page, just a minute. Okay, so now this is a very great example by Geeks4Geeks. You just need to search DOM tree. You just need to search DOM tree on Google and you'll find this article. So you can see DOM simply stands for, by the way, document object model. So I wanted to show you this diagram. So here you can see that this is a tree representation of a website, or you can say a web page. Okay, so you can see first the document is loaded, then links, forms and anchors are loaded, and then you can see inside this forms we have text area, checkbox, radio. So you must have heard about these HTML basic tags. So there are a lot of tags. So you can see that this is actually loaded, always loaded in a tree format. First the main thing will be loaded, then the document will be loaded, and then different kind of parts of the HTML page will be loaded. So you can see that this is actually a tree structure. Okay, so this is a very great example. And similarly, the hierarchical nature of the trees allows efficient searching, insertion and deletion operations, which we'll be covering in the next video. All the operations will be covered in the next video. Today we'll be only covering the theory part of that. Okay, so very basic operations can be covered very easily in these tree data structure. Okay, also a traversal algorithm, that means I want to visit from A point to D point. It's very easy in trees. Okay, so we'll be exploring that later on. So now what are the applications of tree data structure? First was the DOM manipulation, which I told you. You can view any HTML page or any JavaScript file, something like that. Okay, so in Java, in document object manipulation, actually in JavaScript, it represents the structure of HTML or XML page in a tree format, which we have seen right now. Okay, so JavaScript can traverse and manipulate the DOM tree. We can actually manipulate anything in HTML page using JavaScript. Okay, so because of the tree structure, we can cover every part of the HTML page using JavaScript, and we can dynamically update the web page content, handle events, create interactive user interfaces and perform animation. This is only happening because of tree data structure. That's why it's very important. Tree format is very important. Okay, second is the file system, which I told you. The data structure are commonly used to represent file system. In JavaScript, you can use trees to model directory structures, store file metadata and navigate through files and folders. Okay, so you can actually create a folder inside multiple folder and something like that. So it's actually a file system which is actually using a tree format. Okay, so we actually use route it in routing and navigation. If you know something about React.js or AngularJS, they actually use some tree structure to perform routing. Okay, that means suppose I say that visit the user section. The user section can have multiple pages. Okay, so first I visit the section, then user section can have multiple sections more, something like that. User can forgot you If the user forgets his password, then they can go to the forget page, then the user can go to the edit profile page, user can go to the my orders page and something like that. So you can see that routing and navigation is basically used to perform these kind of tree formatted things. Okay, so this is very helpful in navigation also. All right, so data structure tree data structure is also used in artificial intelligence for decision making. Yeah, decision trees, okay, which actually looks like a tree data structure, is widely used in machine learning and artificial intelligence applications. So this is a very important data structure which we are learning right now. Okay, so they represent a series of decisions and their possible outcomes. Like anything can have two outcomes, minimum two outcomes, something like that. either it is yes or no, either it is true or false. So you can see it also forms a tree. Okay, if this happens, something will happen, something will happen. So it's like a tree, right? So you can use it in AI also. And then there are a lot of uses of trees, such as hierarchical data representation. Trees are valuable for representing hierarchical data, parent-child relationship. We also use trees for caching. So caching and memoization. So tree based data structures such as binary search trees or self-balancing trees can be utilized for caching and memoization uh, purposes. They allow for efficient storage and retrieval of computed results and based on input parameters. Okay, so these are some basic applications of tree data structures. All right, so now enough of the basic theory part. We'll be learning about some more typical concepts which people find difficult. Okay, so if you have your theory exams in college, and when I had this subject, when I had the data structure subject in my college, these kind of topics were actually confusing. Okay, pre-order traversal, in-order traversal, and post-order traversal. What are these? Okay, what are these? So I'll go one by one. So you can see I have simply displayed a very basic tree. Okay, in the coding format, you represented something like this. Okay, so you can see that we have a very basic tree. A has childs B and C, B has child D and E, C has child F and G. So you can see this is a very basic tree. So traversal simply means going from one place to other place. Traversing the whole tree, it simply means covering each node. Okay, so I hope you understood traversal. So traversal, if I talk about pre-order traversal, so pre-order traversal, you can see that first we'll go from A to B to D. Okay, then we'll cover the second child, that is E. Okay, then we'll go to the next part, that is first we'll cover the left side, then we'll be covering the right side. So you can see first we covered the left side, then we covered the right side of E, then we covered the right side of A, C part. Okay, then we covered the left side of C, that is the right side of G. Okay, so you can see that we have covered, first we have to cover the left side, then we have to cover the right side. Okay, this is known as pre-order traversal. Okay, so pre-order traversal involves visiting the nodes in the following order: from root to left subtree to right subtree. Okay, in pre-order traversal we start at the root and visit each node before its children. Okay, so you can see we have visited each node from its children. Okay, you can see we visited each node, and first we have visited the left subtree, then the right subtree. Okay, so I hope you got the basic definition of pre-order traversal. Now what is in order traversal? So in order traversal, you can see we have visited from D, that is from bottom, to B to E. Okay, then we'll go to the next parent, that is A. From A to the child. Okay, you can see that it's something like this. So you'll be first covering the left side. Okay, first you will be covering the left side from the bottom. Okay, so you'll go to the top, then we will be starting from the right side, but again from the bottom. Okay, and from the bottom and from the left side of the bottom. So you can see again I have started from F, C, G, then if anything is pending will be covered like that. So in order traversal involves visiting the nodes in the following order. So we have covered the left subtree first. Okay, then we have covered the root, then we have covered the right subtree. So you can see it works something like this, but the covering will always be from bottom in this case. Okay, so we have covered like this, and we start at the leftmost node, that is the D. Okay, and visit each node in the left subtree. So you can see we have visited each node in the left subtree in this order, and then the nodes in the then we visit the root. Okay, we visit the root, and then we visit the right subtree in again the same order, F, C, G. Okay, so you can see from left to right we are visiting. All right, so this is a very basic in order traversal format. Now what is post order traversal? So post-order traversal involves visiting the nodes in the following order. First, you visit the left subtree. Okay, so you can see we again have D, E, B. Okay, then we have F, G, C. So you can see we are covering each layer. First is D, E, B. Okay, this parent child is completed. Then we cover from F, G, C. Then above that we have A. Okay, so you can simply see that it's actually covering like D, E, that is siblings, then its parent. Okay, F, G, siblings, then its parent. then these are covered, then we'll cover its parent. Okay, so you can see it's something like this. So its format is very easy: left subtree, right subtree, and root. Okay, so in post order traversal, we start from the leftmost side and visit each part of the left subtree, then followed by the nodes of the right subtree, and then the finally root. So we visited it something like this. Okay, so each traversal order provides a different way of visiting the nodes of the tree, resulting in different sequences of nodes to be processed. These traversal orders are useful in various scenarios, such as printing the tree data structure and performing certain operations on the node. So if you have to perform some operation on each node or different nodes, then you will be using some kind of traversal. So you can use different traversal techniques for separate purposes. Okay, so it is important to note that these traversal orders apply specifically to binary trees. Okay, but similar concepts can be extended to other kind of trees as well. So these are mostly used in the binary trees. Okay, so we'll be looking what is binary tree. So binary tree is simply nothing, a leaf. Okay, you can see that a parent a parent can have at most two children. You can see it has at most two children. Okay, A is a parent. Okay, and its children are B and C. So you can see B is a parent and its children are D and E. C is a parent, it has children F and G. Okay, so you can say that if G wasn't there, then still it was a binary tree because it has at least one child. Okay, it has one child. That means you can't have more than two childs. Okay, if there was a third child, that means if there was another child named as H, okay, for this case, then it won't be a binary tree. Okay, so you can have no child, that means D has no child, or you can have one child at least, or you can have at most two children. Okay, that is D and E, F and G, something like this. Okay, this is known as a binary tree. All right, so we'll be looking into types of trees which are available. So mostly you will be learning these kind of trees. So a general tree looks something like this, where we don't have any restriction. We can have any number of children, any number of parents, something like this. Okay, so a general tree data structure has no restriction on the number of nodes. It means that the parent node can have any number of children. Okay, not only two, you can have three children, four children, something like this. Okay, so this is a general tree. Now what is a binary tree? I told you that you can have at most two children. Okay, if you don't have any children, like you can see G does not have any children, then it's a valid tree. Okay, it's a valid binary tree. So you can say that if I talk about F has one children, then it's still valid. If I talk about B, it has two children, D and E, so it's still valid. But if it had a third child, that means suppose it had X as a child, okay, then it wasn't a valid binary tree. So you can say that each node specifies has a maximum number of two childs. Okay, two or less child, it can have two or less childs. Okay, so a node in binary tree can have a maximum two child nodes. Okay, in the given tree diagram, node B, D and F are left children and E, C, G are right children. Okay, so now what is a balanced tree? So if the height of left subtree and right subtree are equal, okay, so you can say that this height, you can say what is the left height. You can see that the height is 2. You can see that the height of this tree is 2 from the left side, and from the right it is 3. So it's almost same because the difference is 1. Okay, so you can say that if difference is 1, it can be considered. If difference is same, that means it has two edges. Okay, it has two edges. If I talk about height, then it's still a balanced tree. If there is a difference of one edge, then it's still a balanced tree. If it has a difference of two edges, that means if it was longer, the right side was more longer, then it won't be considered as a balanced tree. Okay, so I hope you understood what is a balanced tree. So now what is a binary search tree? So this is very important. We are going to learn this tree because this is the most used one, and we will be working on this binary search tree operations on it in the next video. So as the name suggests, binary search trees are used for various searching and sorting algorithms. The examples used, we will be using AVL tree, red-black tree. It is a non-linear data structure and it shows the value of left node is lesser than the parent, while the value of right node is greater than the parent. Okay, what I'm talking about is, let's see what is a binary search tree because this is very important. Okay, so a binary search tree is a binary tree. Okay, first of all, it's a binary tree. It has a few more rules. Okay, so you can see that the left subtree of the node contains only less nodes than the parent. Okay, so you can say that if I talk about 8 is the root or parent. Okay, so you can say that 8 elements lesser than 8, you can see that the elements lesser than 8 are always on the left side. Elements greater than right elements greater than 8 are always on the right side. So you can say that this is known as a binary search tree. Very basic definition. Okay, so left subtree will always be smaller than the parent, right subtree will always be greater than the parent. So again, if I talk about, okay, so again, if I talk about this, you can see that it's something like this. Okay, so in the next video, we'll be actually seeing what's the logic behind this. You can see that we have these elements 1, 3, 6. Okay, we have 4, 6, 7. So this order is something like smaller element, middle element, bigger element, smaller element, middle element, bigger element. Okay, so I hope you are getting the difference. What's the usage of binary search tree? Okay, so searching actually becomes a lot easier in binary search tree because its order is very specific. Okay, so it's a binary tree with some more rules. So the right subtree of a node contains only nodes which are greater than. Okay, you can see these are greater than the parent. Okay, so the left and right subtrees each must also be a search tree, binary search tree. Okay, so you can see that this is also binary search tree. This is also binary search tree because left side is smaller, right side is greater. This is also binary search tree. This is also binary search tree. So you can see it works something like this. Okay, so you might have noticed that after 10 14 is on the right side, even it is only a one child, it's in the right side. Okay, so the format is very important. You need to always display in this format. Okay, so searching an element in the binary search tree is easy as we have a hint that which subtree has desired element. You can see that this is desired format. We know which element could be in which direction. Okay, so as compared to array or linked list, insertion and deletion operations are very much easier, faster in binary search tree. That's why we use this binary search tree. If you have complex data, for searching, you will always be using trees or different kind of more complex data structures, but they are really helpful. Okay, universe, bhaiya, please speak in Hindi also. Yeah, actually, previously, whenever we had sessions before, I actually tried to speak in Hindi, and I preferred that before. Actually, Hindi is much better than English, but a lot of people are actually from other kinds. Like someone is from South and someone is from uh, not from India, somewhere else. So that's why I'm speaking in English, but I prefer Hindi more, honestly. Okay, yeah. So now we are towards the end of this video. In the next video, we'll be covering a few operation. Okay, so what are the operation in binary search tree? We have insert, delete, search, in order traversal, pre-order traversal, post-order traversal. Okay, so we have you know what is insert, what is delete, and what is search, and we have covered these three right now. So we'll be covering these three operations in binary search tree, and there can be more operations which are required for it. So we'll be covering everything which is required in binary search tree using JavaScript. Okay, so I hope you understood this video. And before ending this video, in the live chat, if you have any doubts, you can still ask me regarding normal data structure or any kind of technologies if you want. All right. So by the way, if you have any doubts regarding web development or app development, you can still ask me that. I am an expert in technologies like MongoDB, Node.js, React.js, Express, React Native, GitHub, AWS, Redux, Angular, Next.js, Firebase, C++, and Python. So you can ask me doubts if you have regarding these. And if you want to contact me, you can contact me on Instagram at the rate Harshal underscore 3011. All right, you can also message me on LinkedIn. Okay, yeah. So before ending this video, in the live chat, you can see that we have a link of data structures and algorithm course in JavaScript. So you can visit that link. Also, you can check out the description for that. The same link is available in the description. So if you visit that link, it will take you to this page. So this is a paid course which will teach you data structures and algorithms in JavaScript. So if you want to learn data structures and algorithms in JavaScript, then you can refer this course. And this is actually a very much defined course. You can see that a lot of things are covered here, and everything is covered actually. So in a structured order, everything is covered. So you can check out this. And the instructor is actually Sandeep sir, who is the founder and CEO of Geeks4Geeks. So he has a very great teaching experience in this field. Okay, so I hope you understood this video, and in the next video we'll be covering the operations which are required in binary search tree. All right, so I hope everything is fine, and if you don't have any doubts, I can end this stream. All right, so that's it for today. I will see you in the next one. Till then, have a good day. Bye bye.